The continuous growth formula looks at what would happen if you took your compound interest formula and you noticed how it increases if you have more compounding periods. So monthly would be 12 times. If you did it daily, it would be 365 times a year. If it got compounded every hour, it would be even a bigger number. Every second, a bigger number. And so the continuous growth formula says, what would happen if you were just always getting money? Your bank account would just be like continually rising to the millionth decimal place, and you'd make 1/1000th of a cent, and the next second you'd make interest again, and you make interest on that new billionth of a cent, and it'd always be growing and growing and growing. And what happens is the formula changes from 1 plus r over n to the n to e to the r. So the number e, that 2.7 number, shows up in continuous growth. So we're going to do some questions with this. Find the amount of money earned if $2,000 is invested at 5.5% interest for 10 years if the interest is compounded quarterly or if the interest is compounded continuously. And we're going to start with the quarterly one, because that's the formula we've used already. If you plug everything in, A, 2,000 is the amount, interest rate is a decimal, quarterly means 4 times a year for 10 years. It's a pretty good thing. You made $1,400. Now, if it's compounded continuously, that means you're making interest on interest all the time. Compounded quarterly means that you only get paid interest 4 times a year, and you only have an opportunity to make interest on that interest after that time. So over 10 years, this number is going to be bigger. How much bigger do you feel it's going to be? $10 bigger? And you say a lot. Is $10 a lot, or are you thinking more than 10? $10 is a lot? You ready for the result? $13? It is. How did you get that? Did you look ahead on stuff?
I didn't.
Oh, you figured it out. But now, for those of you that didn't figure it out, was your gut saying that it was going to be like a lot more than that? It's actually surprising that it is just a little bit more, especially over 10 years. Now, a key thing to learn from this for you in your life is the biggest factor that's going to be changing the amounts is the interest rate. When you borrow money from the bank, if you can negotiate a smallest interest rate possible, that could save you thousands and thousands and thousands of dollars. I would say that so here's another one for you. An investment of $200 is compounded continuously. Now, it used to be that that continuous formula was on your formula sheet, and so you would have to know that the fact that this question said continuously to use that formula. But now the formula is going to be given to you. You would know that you were using, I like to call it the PERT formula, and you would plug in everything. 200 initially, it's now worth 235 over 3 years. The only thing we don't know is R, and so we need to solve for R, and R is in the exponent. How do we solve for things when they're in the exponent? We have to take the log of both sides. Now, since there's a base E, it makes sense to take the natural log of both sides rather than the log of both sides. It will still work if you take the log of both sides, but if I take the natural log of both sides, the 3r can come out in front, and the natural log of e is just equal to 1. And so when I want to solve for r, all I have to do is divide by 3, plug that into my calculator, and get a value for r. All right, let's check how you did. Plug things into the PERT formula. Again, I would start by dividing both sides by 1300 to make it your exponent or your power all by itself. Then take the natural log of both sides. Natural log of e is 1. That exponent can come out in front with your log law. Divide by 0.53. And solve and start to practice rounding to 3 decimal places, because you have to round to 3 decimal places, and remember to include your units. Anybody know what you get if you don't remember your units? Not an E10, close. Not an E7. No, there's no E12s. E10 is the highest. It's an E5. Another application of the PERT formula is with population and continuous growth with population. When populations get large enough, like the human population, often they use a continuous growth that there's always babies being born, there's always people dying, so the population is growing at a certain rate continuously. Right? If you look at statistics, during this class in the world, how many babies were born? How many people died? Let's think about the babies, it's not as morbid. But a lot of things have happened in the last hour while you were learning math. That doesn't sound like I should have been somewhere else. No, a lot of people are missing out on what we're learning in math because they're busy being born. Anyways, continuous growth for population. So again, we're going to use exactly the same formula, PERT formula. And in 1981, the population of Vancouver was 1.38 million. It's been growing continuously at 1.7%. What is the population going to be in 2011? So we want to find the amount. We know the initial is 1.38 million. The rate 0.017, and how many years will it be in 2011? 30 years later. We can type this into our calculator exactly as we see it. And boom, to the nearest tenth of a million would be 2.3 million. When will the population reach 6 million? So again, we have our PERT formula. And when it's asking when, we're solving for time. So we would need to put in values for each thing. We have 6 million here, 1.38 million. E, the rate is 1.7%. And time. At this time, I would divide both sides by the 1.38 million. Can you see that 4 zeros would cancel out when you divide? So I'm going to just write this side as 600 over 138 equals e to the 0.017t. And since the base is e, I'm going to take the natural log of both sides. So the natural log of this side. And when I take the natural log of this side, the exponent could come out in front using one of our exponent laws. And of course, the natural log of e is equal to 1. So solving for t, I would just need to divide by 0.017. Go to my calculator, use my fraction button, natural log 600 divided by 138, divide by 0.017, 86.45. Now, when I get 86.45, I guess I should have 3 decimal places, 452. When I get 86.452 years, does that mean in the year 86, the population of Vancouver is 6 million? No. What year would that be? So I could write a statement, in the year blah, 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 the population of Vancouver will be 6 million. What does that 86 years mean? 86 years. 86 years from the initial year. What was our initial year? 1981. So if you had 1981 and added 86 years to that, you're going to get to the in the year 2067. And so these kind of models can be helpful for cities or the world in that saying, if things continue the way they're continuing, we're going to have a problem. Or how are we going to deal with that in this area? When the population of a herd of gophers was first studied, it was 15,000. 6 years later, the population was 18,000. If the population grows continuously, and of course now, I mean, this hint would have told you in the past that you would need to use this formula. Now they would give you this formula. How long would it take to triple? So we have a problem here, because if we go to what the question is asking, which is how long, what do we need to solve for? Time. So that would work if we could put numbers in everywhere else. Now, for something to triple, you could pick any amount for p. You could start with the 15 or the 18 and triple it to get the amount to be tripled. But the problem is you don't know t, and you don't know r. So if you want to solve for t, you need to put in numbers for everything else, but we don't know r. So this is the most complicated kind of question, because you don't know t and you don't know r. So what do we have to do? We have to find r first. Do I have enough information to put numbers in for everything else except for r? Yes. Because I know that 6 years after an initial time, it's 18,000. So I could put in 18,000 for the amount, 15,000 for the original, e to the r, and that happens 6 years later. So I can make an equation where the only thing I don't know is r. Are you okay if I divide both sides by 15,000 that I just write 18 over 15? You could reduce that if you wanted to 6 over 5, but you could leave it as 18 over 15. And on this side, are you okay with r times 6, that I write it as 6r? More often we write the variable after the number. How do we solve for an exponent? Take the log of both sides. Since it's an e, excuse me, that's going to be nice and loud, and I think I sneezed right into the microphone. So if you were sleeping, you'd wake up at this moment? No. Okay. Anyways. Oh, man. When Sam realizes he doesn't have these notes and he watches the video later, he's going to be referenced in it. Okay. Oh, there's a. You should get, this angle is probably the best. If you're looking for the picture, you can get both of them. Okay, anyways. Yeah, we gotta plan. Slam the door, I'll get in trouble with something. Like this. Like this. Like this. Yeah. I did that once. So natural log of e is 1. And so we can solve for r to be the natural log of 18 over 15, all divided by 6. We're going to go to our calculator, type that in. Natural log of 18 divided by 15. All divided by 6. And we get a value for r. We're going to need all of those decimal places. You can store it as x, but if you want to like even use like the letter r, you can store it as r if you'd like. And so often I will write just dots after that to say I'm keeping all of the decimal places for later. And now we can find t. If we wanted to triple, we could use any number here. Usually people get stuck on using the number that's there. So the 1500 was given, or the 1800 was given. I would choose 1500 because it's easier to triple. E to the r, which we now know is this, and we can solve for t. Now the reason it doesn't matter what number you choose is because if you now divide by 15,000, you'll just get 3. And if we want to solve for t, we'll take the natural log of both sides. That 0.03 times t would come out in front. You get natural log of e, which of course is equal to 1. And so we can go to our calculator and do the natural log of 3 divided by r. Now, I could use the letter r, but since the number's still there, I could just go second answer as well. That's probably even quicker. And get that t is 36.154 years. So it'll take about 36.154 years to triple. All right, anything else wrong with this question? No, all good? Okay. There was one other tiny little thing wrong. It's not a herd of gophers. Does anyone know what a group of gophers is actually called? It's not a pack of gophers. It's not a herd of gophers. It's called a colony of gophers. Okay, we need to make sure that we know our animal names. I think this is unique to English, that every group of animals has its own unique name. So I've got one for you to try. A group of rhinos is called a crash of rhinos. That is a cool name. Do you know any other cool ones? A gaggle of geese? A murder of crows? Yes. Okay, I will, while you're working on this, I will look up animal names. Oh, a zeal of zebras. Look at that. A napping of Nikos. He's gone. He was back for a second. But he came back with a zeal, so that's 28.56 years. R to be 0.02 ... Yeah, if you want to go right from 1 to 2 there, you could do that.